Good morning. Today is Wednesday, February the 12th, 2025, and you're watching Make Programming Fun Again. And today I have originally planned to cover Go 124, but I have decided that a coverage of Go 124 would be too short, as I have decided to make my videos an hour long each. And I have decided to instead cover UUID version 7, and I would like to continue on yesterday's example where we implemented a single program querying a SQLite database, and I'm going to expand on that to also cover using UUIDs as primary keys. So first, let us discuss what UUIDs are. If you come from the C# world, you may know UUIDs as GUIDs or GIDs, and it stands for Universally Unique Identifier or Globally Unique Identifier. And the idea behind UUIDs is that they provide there are so many possible UUIDs that even if you generate them randomly on machines that do not communicate with each other, there is so much randomness that even with all the birthday problem shenanigans, the actual possibility of two UUIDs colliding is next to none. So you can almost safely use UUIDs as primary keys for anything you want. So for example, let's say let's even say we're doing something like we want to generate a UUID for every SQLite database in existence. And if there is a trillion, that means you're going to need 1 trillion UUID databases, and even so, we can just safely randomly generate a single UUID for every single SQLite database in existence, and it probably would not collide. And that said, there have been several versions of UUID standard and of UUIDs, and my personal favorite is UUID version 7. So before UUID version 7, you would most likely use UUID version 4. And all versions of UUIDs are currently defined in RFC 9562, and RFC stands for Request for Comment. And RFCs are standard documents standardized by IETF, the Internet Engineering Task Force, and they are documents that define several standards, like things like URL or technically URIs, or things like HTTP, or probably things like JSON. Everything is defined in those RFCs. So the UUID version 4, it was commonly used as primary key in databases by some people, and it basically consists of 128 bits of random data, between which you put some basically you put a few bits that indicate the version. And the problem with UUID v4 is that maybe let me show you an example of some UUIDs. So I'm going to quickly use Elixir for that. I'm going to install a library that generates UUIDs, and in here UUID UUID6, UUID4. Okay, so this looks completely random, and it most likely is pseudorandom. And the problem is that if I generate subsequent, like for every subsequent call of UUID4, I'm going to get a different, I'm going to get a UUID with a different beginning, and they do not sort. I generated this one first, and this one will sort before it, and this one will sort before that. So this is terrible for database indexes. This is a terrible choice for a primary key, because this way, every time you generate a new value, you will probably need to rebuild your primary key, or at least you may have to. If you try to put a new value into primary key index somewhere in between, it's going to take a very long time. And also with UUIDv4, you have no indication as to which record was created when. So this is obviously not ideal. So UUID version 7 was proposed. I mean 6, 7, and 8 were proposed more or less at the same time. Anyway, we're going to use UUID version 7, and we're going to try and implement it in C, and then we can try to use it in a SQLite database. So UUID, it's okay. So UUID UUIDv7, it consists of a timestamp, which we put here, a big endian in this first I think in the first 6 bytes. Then we put a binary marker for a version, and then what is var? Okay, in this, so UUID is 120 bits long, and inside those 120 bits we have several fields that have to be filled, and the first part is going to be a timestamp, and that's a millisecond timestamp, beginning, like the number of milliseconds starting from January the 1st, 1970 UTC. So a Unix timestamp, but in milliseconds, and then we are going to get some randomness. So we could try and start implementing this. So I'm going to create a directory called UUID, and in here I'm going to copy the gitignore file from video 11, and let's try writing some code. So first we're going to need a way to generate pseudorandom data. So for cryptographically secure applications, you should use a cryptographically secure pseudorandom number generator. And since I'm on Linux, I'm going to use a system called getrandom. As far as I know, it is not available on macOS. So on macOS, you may want to use arg for random. And yeah, technically we could try to use either one. It is available in glibc 2024. What do we have for glibc? I don't know how to check the let me check my current version of glibc. Oh, it depends on the particular compiler. Okay, what does it say? It does not say it. What does LD say? It also does not say. What does LDD say? Okay, so we are on glibc 236. So this arc for random calls should be available. Anyway, we're going to need a Unix timestamp in milliseconds, and we are going to need a random number generator. So I'm going to have to look for a way to get a millisecond timestamp in C. Get time of day. What does get time of day say? Man, get time of day. Okay, so it seems that this is a good way to get milliseconds in okay, this is a function call called getTimeOfDay, and it seems like it returns a timestamp, and it contains the seconds and microseconds. So let's see. Struct timevar restrict tv struct timezone nullable restrict tz. So we basically just need it in UTC, right? And this one is available in systime. Int main. Let me just try and get the current Unix timestamp in seconds, and then we can try to see what we get with regard to microseconds. Struct timeval timestamp, and we get time of day ts, and we point the timestamp to now, and then we can try to printf the time of day tvsec. Okay, and return 0. Okay, and then we make UUID. It prints the current Unix timestamp. I think it works. We could probably, yeah, I think this is more or less correct, right? Yeah, I guess. So clock get time. What does clock get time do? The function clock_getRes finds the resolution of the specified clock ID, and if res is not null, stores it in the struct timespec pointed to by res. The resolution of clocks depends on the implementation and cannot be configured by a particular process. If the time value pointed to by the argument TP of clock set time is not a multiple of res, when it is truncated to a multiple of res. The functions clock get time and clock set time retrieve and set the time of the specified clock ID. The res and TP arguments are time spec structures. The clock ID argument is the identifier of the particular clock on which to act. A clock may be system-wide. Okay. All implementations support the system-wide real-time clock, which is identified by clock real-time. Its time represents seconds and nanoseconds since the epoch. When its time is changed, timers for a relative interval are unaffected, but timers for an absolute point in time are affected. More clocks may be implemented. Okay, we want the clock real time. So what does this? Okay, clock get time, time spec TP. TP. Okay, clock get time, clock real time to TP, and then let's say printf ld TP. Okay, it seems like they do kind of do a similar thing. Yeah, so I think either of these would work, but we could probably use time.h rather than like which one is this even? Okay, I'm not going to use the time I'm not going to use get time of day because it is implemented in sys/time.h rather than time.h, so I assume it may be system specific. Standard. Okay, BSD POSIX describes get time of day but not set time of day. POSIX 2008 marks get time of day as obsolete, recommending the use of clock get time instead. So they would both work, but clock get time is recommended. So I'm going to need I'm going to use the uint. I'm going to return this as int64t get epoch use we're going to need we need millisecond precision, right? So int64t okay, so struct time spec TP clock get time clock real time to TP, and then so in TP we now have the microseconds and we have seconds, right? So you can return TP. Wait, that's nanoseconds, okay. And a nanosecond is 1/millionth of a microsecond. What does this? Okay, what does this? Wait, I'm going to comment it out, and in here, what does the microsecond part say? It's nanosecond. Okay, it seems like this is just a part of the it's just a part of this. The nanosecond is just a part of the timestamp, so I can probably do something like return TP second times 1000 plus nanosecond TP in nsec divided by 1 million. Let's see if this works. What does time t stand for? It's long. Okay. In 64t ms timestamp equals get epoch in milliseconds and printf yeah, this looks legit. So for now, I'm just going to assume this is real, and we're going to need a way to output it as a big endian binary. So a big endian binary is basically when a big endian binary is what we would consider what we humans consider natural. A big endian order is the order when the bytes in memory of a computer are stored with the most significant byte at the end, and little endian is what Intel and ARM processors use. And yep, I'm not going to get too involved in big endianness for now. But we are going to need a way to convert this timestamp to a big endian number. So also I'm going to define a type for this UUID thing, and I'm just going to make it a uint8t pointer. Okay. So now we can try like this: UUIDt UUID, and then technically UUIDt is, it should work like this, right? So we have a 16 byte binary, and here we get these here we get the timestamp, and the timestamp we right now, the timestamp we get is it's 8 bytes long, and we want to make it 6 bytes long, because this is what the Unix timestamp thing does. So I could just say for you would basically just use the last 6 bytes. So for 0, int I equals 0, I is less than 6, I plus plus. We want to get the nth byte from the end of this timestamp. So uint 8t byte equals msts. I think we can just get the we can just shift it to the right and select the last byte, right? So I times 8 and so I think you could just say byte is here, and so now if we get this byte and we want to put it at the specific index in there, so you can say UUID index 6 minus I or maybe 5 minus I, I'm not sure, equals byte, and then we can try to output all of these bytes that we currently have for debugging. I is less than 16, I plus plus. So let's see, printf, do we have x? Okay, we do. UUID of I, and then printf new line. So now can we get 2x 0 to x? Okay. I wonder, does this kind of match the UUID syntax we are getting in with a real UUID generator? Yeah, it does. So we are getting 0194F8, okay, and here we also get a similar beginning. So the first 6 bytes seem to be matching. So now we are going to need randomness for the remaining 10 bytes. So let me look at getrandom. We need a pointer to buffer and a buffer length and unsigned integer flags. And what are the flags? If this bit is set, okay, the flags, the getrandom system call fills the buffer pointed to by buff with up to bufflen random bytes. These bytes can be used to seed user space random number generators or for cryptographic purposes. By default, getrandom draws entropy from the urandom source, i.e. the same source as a dev urandom device. This behavior can be changed via the flags argument. If the urandom source has been initialized, reads up to 256 bytes, will always return as many bytes as requested, and will not be interrupted by signals. No such guarantees apply for larger buffer sizes. For example, if the call is interrupted by a signal handler, it may return a partially filled buffer or fail with the error interrupted. If the urandom source has not yet been initialized, then getrandom will block unless getrand non-block is specified in flags. The flags argument is a bit mask that contains 0 or more of the following values or together. Yeah, I don't think we want any of those bytes, so I'm just going to set it to 0. On success, getrandom returns the number of bytes that were copied to the buffer buff. This may be less than the number of bytes requested via bufflen if either getrand random was specified in flags and insufficient entropy was present in the random source, or the system call was interrupted by a signal. Anyway. We need entropy, so include sys random h and getrandom buffer 5. Wait, Alex, with the time size to length, we want 10 bytes and no flags. Oh, and it's UUID in here, right? So you point to, well, you point to the address of a 5th byte. And what is the return value? It is a size t. Return code. Yeah, let's just ignore the return value for now and try to print it. So this looks like random data to me. Great. And no, it does not. The last byte is always 0. So I think we should be starting from the 7th byte, like this. Yes, so now we are filling all the bytes with randomly looking data. And the only thing that is remaining is we need to set the flags on these bytes. So the version is octet 6 at octet 6. So these are bytes 48 through 51 of octet 6. So I assume UUID6 is we're just going to sum it. So we're going to get the 6th byte of this byte of UUID, and we only want its last 4 bits, and we sum it with number 7. Oh yeah, we can just sum it with 0x70, right? So this way, the byte in this place should always, or the first part of that 7th byte should always be 7. So on all subsequent runs, that byte will be set to 7. Okay. And in octet 8, we should set the first 2 bits to 1 0. Okay, that's going to be a bit more tricky. UUID byte 8 equals the 8th byte of UUID, and I think what was it? I think it's 0x pre-f, because we are using the last 2 bits. Yeah, 1, 2. 7, yep. And we sum it with 2 moved 6 bits to the right. I guess this is how it works. And let's compile and print it. I'm not entirely sure if this works, but I guess it does. And we don't need to print the generator, the generated timestamp. Yep, I mean it looks like UUID is just not printed in the canonical format. So now what we need to do is that we need to ensure monotonicity, and what that means is that if I happen to generate with the same node, if I happen to generate 2 UUIDs on the same millisecond, I should not use the same timestamp. I should use the next timestamp in order to ensure monotonicity. So for that we're going to need state. V7 generator, or yeah, UUIDv7 generator. Okay, and in here I'm just going to store the last timestamp we generated, right? Also, what is this? What type are these? These are time t, which are long, and this is also a long. Okay, so I'm just going to use a long in here, and I'm going to define a function that returns a UUIDt. Technically, we probably shouldn't be returning a pointer, since we are going to be, because we are dealing with values that may have to be freed, so it's probably better to generate this value in with just by passing a pointer to it. So I think we're also going to need some sort of a way to return a status code, right? Type dev struct UUID code v7 status, and UUID OK is 0, and UUID error equals -1, because this is what will happen. Oh, and this is an enum, not a struct status. Okay. So now that we have this, we can define a function that returns UUIDv7 status and generates UUIDv7 with a pointer to a UUIDv7 generator and a buffer. like so. So now we can also, yes, we have the last thing in here. So the current timestamp is going to be this. If the last pointer on the generator was less than or equal to, was greater than or equal to MSTS, then we are going to use if the last timestamp used by the generator was the same or greater than the current timestamp, which may happen, for example, if you change time zones or in any way you have modified the clock time. Use next timestamp after the last one plus 1 millisecond. Okay, so now we have its timestamp, and we have our buffer. So put the most significant 6 bytes, 48 bits of the millisecond timestamp in the first 6 bytes of the buffer, big endian. Okay, so we put this big endian in there. Take ith byte from the end, put it at the 5 minus 8 byte e.g. Yep. So basically this will, we start with 0. We're going to get the, and 0 will first get when we shift the timestamp 0 bits to the right, and when we take the last byte in that timestamp at the moment, it's going to be the last byte of the timestamp altogether, big endian. And then when we do it with when I is 0, then we shift it 8 bits to the right. So the last byte is going to be the second last byte, big endian. This is kind of like the natural order for humans, and we have to iterate in, we have to fetch them from the right, but we then put them at we put them in the buffer starting from the 6th byte from right to left. So yep, if you're not familiar with bitwise operations, let me know. I can try and explain some of them. And then we need to fetch randomness. So if RC equals to -1, return -1, return UUID error. If generating random bytes fails, fail the function. Okay. And then we put the markers in there. So UUID6 is like in the 7th byte of the UUID we put we can just copy this part. And in the 2-bit variant field defined by section 4.1 set to 10 B10. Okay. And then we can return UUID. Okay. So now let's see. We can basically try to generate a few UUIDs. So status return code equals generate UUIDv7, and we define a UUID generator. We pass the pointer to it, and we use the destination like this. So UUID. Okay, yep. And let's see if this works. Okay, this is completely wrong. What just happened? So what just happened? Did we pass the wrong pointer or what? Oh, I think it's because yeah, okay. This is because we are returning rubbish. Okay. So we defined a new UUID, but we did not copy it to the destination, and we probably should only copy it to the destination on success. So memcpy what are we copying in here? We pointed to the pointed to the destination like this. Copy and bytes of source to destination. Okay, so if everything works out, we copy this to the destination. Okay, now this seems to work. Okay, and what would happen if we tried to generate several UUIDs? Also, let me just quickly write a function to void debug UUID ID type UUID 21. Okay. So in the yes, so a UUID looks like, what does it look like? I want to get the canonical representation of a UUID. So UUID generator states no. Update motivation, timestamp monotonicity, nope. Collision resistance, example of a UU. Okay, so it's 4 bytes, 2 bytes, 2 bytes, 2 bytes, and then the remaining 6 bytes. So we can say basically for int I equals 0, I is less than 16, I plus plus, we printf the byte as hex, and then if I equals 4 or I equals 6 or I equals 8 or I equals 10, we also print a hyphen, and then at the end we put a new line. So now we can debug the UUID in its canonical form. Great. This looks like a canonical UUID, to me at least. And then let's see what happens if if we generate several UUIDs. I equals 0, I is less than 10, I plus plus, and we can define this in here. Yeah, okay, we can use it. You can use this in a loop. We can make it local to the loop. Like so. And now it defines okay. Oh, we haven't set the state of the gen last equals msts. Okay, so now we also need to set the state. So now if we try to generate several UUIDs within the same millisecond, they should remain monotonic. I'm not sure how well this is defined in this case. It seems like the generation itself takes several milliseconds, and but yes, it does look like quite a solid UUIDv7 generator to me. If you think I'm wrong, let me know. Anyway, this is a UUIDv7 v7 generator, and we probably should write some tests for it. So I'm going to just I'm only going to start on this, and if we want, and I probably should just test that the generator sets the correct version marker, and that it sets the correct variant field. So this is memory copy. This is a function that copies binary data from a buffer to buffer. Okay. I think we need to install, like, in order to write tests, we need to write cunit. And wow, this is old. Yes, I'm going to have to install cunit on Debian. libcunit1 dev, okay. Sudo apt install libcunit1 libcunit1 dev. Okay, I had to mute the microphone so that you couldn't hear my password. It seems I already have libcunit installed. So now if I wanted to write some tests, I'm going to test functions, okay. Test. Does cunit test all of this by default or not? A cunit test is a C function having the signature void test function void. There are no restrictions on the content of a test function except that it should not modify the cunit framework. For example, add suites or tests, modify the test registry, or initiate a test run. A test function may call other functions, which also may not modify the framework. Registering a test will cause its function to be run when the test is run. An example test function for a routine that returns the maximum of 2 integers might look like int max I void test max I. Cunit assertions. Cunit provides a set of assertions for testing logical conditions. The success or failure of these assertions is tracked by the framework and can be viewed when a test run is complete. Each assertion tests a single logical condition and fails if the condition evaluates to false. Okay. So, how do we even start? I think I had an example somewhere. Was it here? Okay. Yeah, this is from another side project I built at some point. So I could probably just say cu init. Okay. This means I need to define a header file for this. And I'm going to say if not defined UUIDh define UUIDh and end if. And in here I'm going to paste all of these, and I'm going to put UUIDh. Okay, a no type int. Okay, so I'm going to also have to use stdint. Okay, and then I'm going to define these functions like so. Okay, so now this function has no business. These functions have no business calling. Actually, this file has no business having a main function. So I guess in the next video we can actually get a test suite working for this. If you want to see, if you have any specific questions, please let me know. If you have enjoyed watching me do random stuff in a language I don't really know, please like and subscribe. If you did not enjoy this video, please let your friends know that you didn't like it so they can watch this video on their own. And I hope you learned something, and yep, see you in the next video.